Let's use the division algorithm to find the decimal representation of 8/17. Now we just simply plug in the calculator 8 divided by 17. We see the decimal expansion, but it's not repeated, at least it's not repeated yet. The decimal's not started to repeat. Clearly we know that it has to repeat, and so the question is, what is it? And how do we get it if we can't just simply plug into the calculator to figure out the full decimal representation? That's what we'll do in this exercise. To get started, we remember that we have a theorem in class that says that if the length of the repeating block is L, then L must be a factor of phi of 17. 17 is the denominator of this fraction, and the function phi is the number of integers that are less than 17 that are relatively prime with 17. In other words, have no common factors with 17. Well, every number that's less than 17 does not have a common factor with 17 because 17 is prime. And so that implies that L in this case must be a factor of 16. So that L is equal to 1, 2, 4, 8, or 16. So this gives us a little bit of help in figuring out the decimal representation. The repeating block must have length 1, 2, 4, 8, or 16. Well, which is it? Well, clearly it's not 1, 2, 4, or 8. 1, 2, 3, 4, 5, 6, 7, 8 takes us to 3, and then the repeating block doesn't start again. And so we can say with confidence that the repeating block will have length 16. Okay, so to do this, we will use the division algorithm, and as follows. We will start by just doing this. Let's take, we know it's going to have 16 zeros, length 16, so let's put in the first 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So we'll take this number. I started with 8 because that's the numerator, and I multiplied by 10 to the 8th power. No particular magic behind 10 to the 8th, except that I have to eventually get to 10 to the 16th. And let's use the division algorithm with 17 and see what the quotient is. So the quotient is 17 times, 800 million divided by 17. And I get a quotient of 47058823, so 47,058,823. Not surprisingly, these are basically the same digits that you see in the representation of 8/17. So 47058823. So 47,058,823, and there's going to be some remainder. Now, to get the remainder, we'll just simply take 800 million minus 17 times 47,058,823, and we get a remainder of 9. Okay, now we'll do the same thing again with 8 more digits for a total of 16. So 17 times, so 1, 2, 3, 4, 5, 6, 7, 8 divided by 17 is 5, 2, 9, 4, 1, 1, 7, 6 point something. And you probably should guess what the remainder is going to be. You might want to pause and think about it before I compute it. So let's get the remainder. 1, 2, 3, 1, 2, 3, minus 17 times 5, 2, 9, 4, 1, 1, 7, 6. And I get a remainder of 8. So I've come back to where I started with 8. Okay, so what I've done here is, let's now take this top line and multiply it by 10 to the 8th. So I have 8 times 10 to the 16th. Multiplying this left-hand side by 10 to the 8th. And that's going to be equal to 17 times 47058823. Then I add on 8 more zeros. 1, 2, 3, 4, 5, 6, 7, 8, plus 900 million. 1, 2, 3, 4, 5, 6, 7, 8. Let me put in the commas so that we can see where we left off. Okay, so that's taking the top line and just multiplying it by 10 to the 8th power. And that gives me the line in blue. Okay, now 900 million is what I see here. So let's do the substitution, replacing 900 million by what's left here. So I get, well, certainly the first part stays the same, so let me just copy that to the next line. So the first part stays the same. Then copying over the next part gives me plus 17 times 52941176 plus 8. Okay, and so that means that if I bring the 8 over to the left-hand side, that is going to be 8 times 10 to the 16th minus 1. And on the right side, I have 17 times, well, factoring the 17, I would get 4 times 10 to the 15th, that's 4 quadrillion, 705 trillion, 800, sorry, I think I misstated that, thousands, millions, billions, trillions, quadrillions, that's right, 4 quadrillion, 705 trillion, 882 billion. Then over here, I would have 300 million plus 52 million for 352 million. 941,176. And therefore 8/17 is equal to that quotient, that big quotient. So there's my numerator on the right-hand side, divided by 10 to the 16th minus 1. And so from the theorem from class, we know that this is going to be equal to 0.4705 882 352 941 176. And that's 15 digits, matching the 15 nines that appear in the bottom. And so we just simply put the bar on top. There's no leading 0 in front of the 4. And so that would be the full decimal representation, which matches what we saw over here. 8 divided by 17 is equal to 0.4705882335, and the 3 here turns out to be 29, and then 41176. So this allows us to, and that 16-digit block repeats itself. So this allows us a way of getting the extra digits after the register, the calculator runs out, being able to get the full decimal representation. You should convince yourself that this is logically equivalent to basically doing the ordinary way of doing long division. So let me scratch out the scratch work up here. So ordinarily, when we do long division, we would get 8 divided by 17, and it would be 0.0. And we would do 4s up here, so 4 times 17 is 68, minus 12, and then the next 0 comes down. The next number would be 7. 7 times 17 is 119. Then 1 comes down, bring down the next 0. 10 divided by 7, that can't work, so you get 0 there. Bring down the next 0. 100 divided by 17, closest you get is 5. 5 times 17 is 85, and so on. And you should convince yourself that you'll get the exact same representation here, 4705, as you did down here, and at some point near the end, you'll get another 8 as your remainder. And when that 8 as the remainder appears, then the decimals, the digits up here will cycle through 4705 again. So you might want to convince yourself that what we see here at 8/17 is equal to this big thing divided by 10 to the 16th minus 1. That is the same logical equivalent as just doing the long division and just waiting until you get a remainder of 8 again when you come out the other end. Let's now look at the second part of the problem to use the division algorithm and a calculator to find the decimal representation of 4,567 divided by 2,624. 4,567 divided by 2,624 starts off 1.7404725561. There's no obvious repeating pattern that we see from the first few digits. So let's go ahead and factor the denominator. We can see that we clearly have a even number in the denominator. So 2624 divided by 2, still even. 2 one more time. Third time. Fourth time. Fifth time. Sixth time. So I get 41 out, which is prime. So I can write this number as 4,527 divided by 2 to the 6th times 41. Okay, so a few observations. We know that the decimal expansion will have a delay of length 6 and then a repeating part. Now, how do we figure out the length of the repeating part? Well, we have a rule that says that the length of the repeating part is going to be a factor of phi of 41. And phi of 41 is the number of integers, less than 41 that are relatively prime with 41. Well, because 41 is a prime number, every single number that is less than 41 has no common factors with 41. And so we have that the delay must be some factor of 40. Now, unfortunately, there's a lot of possibilities here without doing the work. So L could be 1, 2, 4, 5, 8, 10. Let's see, what else? 20 or 40. So the delay will have one of these lengths, and we don't know which one it is until we actually attempt to do it. Okay, so let's get to it. First off, we have 4,5,627 divided by 2,624. So let's use the division algorithm to figure this out. So let's figure out the delay part. So we know that there's 6 digits in the delay. So 4, 5, 6, 7, and let's multiply that by 1,000,000. And let's figure out the quotient when dividing by 2,624. Probably need more space than that for the quotient. plus the remainder. One, two, three, 1, 2, 3. So the calculator is big enough to handle that. Divided by 2624. And we get a quotient of 1740472. Now let's figure out the remainder. 4, 5, 6, 7. 1, 2, 3, 1, 2, 3. Minus 2624 times 1740472. And the remainder is 1,472. Okay, so this is the delay, and now we're going to attack the repeating part. And so when I get this remainder repeated again, that means I've found it. All right, let's see if the delay has length 1. So 1472, let's multiply that by 10. And if the remainder happens to be the same, then I've got it. So 14720 divided by 2,624 is 5, with the remainder of 1,600. Well, that's not repeated yet, so let's see if the delay has length 2. 1,600. Then I multiply that by 10 and divide by 2,624 to figure out the quotient and remainder this time. So 16,000 divided by 2,624 gives me 6. And the remainder will be 256. Okay, so I still haven't repeated yet. So now we'll see if the length is 4. So I've already done 2 digits, so let's go 2 more digits. So it's 256, and this time we'll multiply it by 100. So 25600 divided by 100. 25600 divided by 2,624 gives me a remainder of 9. And actually I'll put 09 here to remind me that I multiplied by 100 on this step. And the remainder is 1,984. Okay, so I've tried 1, 2, 4. Now let's try to see if the length is 5. And if that doesn't work, we'll try 8 and 10 and so on. Okay, so I increase the 1 more digit, so I multiply by 10 now. So I take the old remainder, 1,984, multiply that by 10. $1,984 times 10 divided by 2,624 gives me a remainder, a quotient of 7. And then the remainder is 1,472. And we notice, of course, that this matches the remainder that we started with. And so if we continue the pattern, the digits will start repeating. Okay, so therefore we are now in position to write down the decimal expansion that 4,567 divided by 2,624 equals, let's start writing this out, 1740472. Now I multiplied this first step by 1,000,000, so I need to go over 6 decimal places. 1, 2, 3, 4, 5, 6. So the decimal point goes right there. And then the digits that repeat will be 56097. And let's check to see if that actually looks right. 4,567 divided by 2,624 gives 1.740472. So that's the terminating part after that delay after 1, 2, 3, 4, 5, 6 places. And then the repeating starts here on 5, 5, 6, and then the calculator doesn't show the extra digits, but the repeating part goes 56097 bar. And so that is the answer. It is possible to do this problem by expressing the denominator in the form of 10 to the r times 10 to the l minus 1. It is a bit painful to do it that way, but it is possible to do it that way. And I encourage you to try that on your own to see if you're able to do that.